Two machines can load the same model and produce completely different answers to the question. Which one is faster? One wins the first token. Another wins sustained generation. One fits the model but runs it slowly, another cannot fit it at all, and a third wins only because its software stack supports the optimized format. That is why buying local AI hardware from one compute number is a mistake. The useful comparison has four axes: capacity, bandwidth, compute, and ecosystem. Capacity answers whether the model, cache, and runtime fit. Bandwidth answers how quickly large amounts of model data can move during generation. Compute answers how quickly the machine performs the math, especially during prompt processing training and large matrix operations. The ecosystem answers whether your model and workflow can use the hardware efficiently in the first place. Now compare Apple Silicon with MLX against NVIDIA's DGX Spark. MLX is Apple's open-source array framework, optimized for Apple Silicon. Its defining advantage is unified memory. The CPU and GPU operate on the same memory pool, so MLX operations can move between them without the explicit host-to-device copies common in a discrete GPU system. That makes a Mac unusually simple for local inference. Install MLX, use MLX LM, download a compatible model, and the framework can take advantage of Apple Silicon's shared memory. Quantization reduces the weight footprint, making larger models practical on a machine that would not hold the original precision. Apple's M5 research also demonstrates why the 4-axis model matters. In its published tests, time to first token benefited strongly from the M5 GPU's neural accelerators. Later token generation was described as memory bandwidth bound on the tested architectures. The M5 system's higher bandwidth helped, but the two phases of inference did not scale in exactly the same way. This is the first buying lesson. Do not ask for 1 tokens per second number. Ask separately for prompt processing, time to first token, and sustained generation at your context length. Now NVIDIA DGX Spark. DGX Spark is a compact Grace Blackwell desktop system with an integrated GPU and a 20-core ARM processor. NVIDIA documents 128 GB of unified LPDDR5X memory with 273 GB per second of bandwidth. NVIDIA says a single system supports models up to 200 billion parameters, with a dual Spark configuration extending that claim to 405 billion. That is a capacity statement, not a promise that every 200 billion parameter model will be fast, fit at every precision, or leave room for a giant context cache. The Spark advantage is the NVIDIA software world. CUDA, PyTorch, Tensor RT-LLM, NGC containers, and the surrounding profiling and deployment ecosystem matter. If your workload already depends on CUDA kernels or NVIDIA-optimized inference software, compatible tooling can be worth more than a theoretical hardware win. But Spark is not the same thing as installing the fastest consumer RTX card. Unified memory provides capacity, while its bandwidth and system design target a compact AI development machine. A discrete desktop GPU may deliver stronger throughput for a model that fits entirely in its VRAM. It may also hit a hard wall on a larger model that Spark or a high-memory Mac can hold. Capacity and speed are different products. Here's the practical workload split. Choose a Mac with MLX when you want a quiet daily computer that is also a strong local AI workstation. Your models and tools support MLX. Privacy and portability matter, and unified memory lets you reach a model size that a conventional laptop GPU cannot. MLX is especially attractive for local experimentation, inference, adapter fine-tuning, Swift applications, and Python workflows built around Apple Silicon. Choose DGX Spark when the NVIDIA ecosystem is part of the requirement. You need a compact Linux-based CUDA development environment. You want 128 GB of unified capacity, or your work must transfer toward NVIDIA deployment infrastructure. Choose a conventional NVIDIA workstation when maximum throughput on models that fit in VRAM matters more than unified capacity, and the power, noise, desktop form, and component complexity are acceptable. Choose cloud compute when the workload is occasional, requires much larger multi-GPU systems, or changes faster than your hardware budget can follow. Now build a buying worksheet before comparing prices. First, name the exact model and precision. A 70 billion parameter model is not enough. 4-bit, 8-bit, and 16-bit formats have radically different memory demands. Second, choose the context length. The key value cache grows with usage. A model that fits at a short prompt may fail or slow down during a long coding session. Third, measure the phase you care about. Interactive chat needs low time to first token and reasonable generation. Batch summarization may care about total throughput. Fine-tuning cares about memory, compute, and supported training methods. Fourth, list software constraints. Does the project require CUDA? Is an MLX conversion available? Are the kernels optimized for ARM, Metal, or Blackwell? Can the team debug the chosen stack? Fifth, account for the entire machine. Storage must hold model copies and quantizations. Memory must leave headroom for the operating system. Power, cooling, portability, remote access, and warranty affect daily use. Sixth, test the real workload. Vendor benchmarks are useful evidence, but they use selected models, precisions, prompt sizes, and software versions. Your codebase, cache, batch size, and runtime can reverse a chart. Run that test long enough to see heat and memory pressure, not only a 30-second launch. A machine can post an excellent cold benchmark and then throttle, page, or compete with the rest of your development tools during a real session. There is no universal Apple versus video winner because local AI is not one workload. Apple's advantage is a tightly integrated computer where MLX can exploit shared memory with low setup friction. DGX Spark's advantage is high unified capacity inside NVIDIA's AI software ecosystem. A discrete RTX system can win raw throughput inside its VRAM boundary. Cloud systems win elasticity. So buy for the bottleneck. If the model does not fit, buy capacity. If generation is too slow, examine bandwidth. If prompts and training are slow, examine compute. If nothing uses the hardware properly, fix the ecosystem choice. The most expensive local AI mistake is buying a benchmark champion for a workload it cannot hold, or buying a capacity champion and expecting the throughput of a completely different class of GPU. Capacity decides whether the race begins. Bandwidth, compute, and software decide how the race ends.